You can do.
I watched the entirety of Ghostbusters.
You're younger. You probably had it in.
Pero ya sacamos de la cuestión de práctica.
Say. Ça va.
I did stick with it.
Bien. Oh my God. You're very close. John, that's the last one you have finished that right back. I wish I had known that in graduate school. I sat in it for a week.
I don't have 15 minutes. I'm just gonna. And just wanna do the demonstration. Yeah, we can take 15 minutes to make sure everyone has. Good. Sorry. And if, do you think anyone else wants to say anything?
Muy buenos días. Estamos ya a punto de iniciar esta segunda jornada. Vamos a iniciar el seminario web en Zoom. Y bueno, muy buenos días a la audiencia aquí presente y a la que se encuentra en Zoom. Esta sería la segunda jornada del taller de entrenamiento Creando Capacidades sobre herramientas y metodologías basadas en ciencia y datos para la toma de decisiones en la Cuenca del Plata. Y bien, como un recordatorio, la sesión está disponible tanto en Zoom como personas en el salón y tienen traducción simultánea disponible en inglés y español. Para los participantes de Zoom, les recordamos, por favor, hacer clic en el botón de interpretación y seleccionar el idioma de su preferencia. También está en el Zoom habilitado la función de preguntas y respuestas a lo largo del día, así que por favor, si necesitan apoyo técnico o alguna consulta que tengan para los panelistas, lo pueden hacer a través de esa función. Y para el equipo que está aquí en el salón, les recordamos que pueden levantar la mano y nosotros les hacemos llegar el micrófono para cualquiera de las preguntas. Para los headsets que están utilizando, les recuerdo que el botón presionando el botón tienen acceso al idioma inglés y quitando la presión del botón sería español. Vale. Vamos a dar un recorrido sobre la agenda del día de hoy. Ayer fue un poco más didáctico sobre la introducción a la teledetección hidrológica. El día de hoy ya vamos a empezar un poco con la práctica. Esta mañana la vamos a dedicar al tema de precipitación. Y bueno, primero, los primeros 5 minutos, mi colega Perry del equipo del ISAT, vamos a dar como un recorrido al tema del GitHub para la instalación y demás. Y luego iniciamos con el doctor Venkat para la descripción general de los objetivos del GPM, medición de la precipitación global. De 10 a 11 tenemos el análisis y discusión de precipitaciones. Y luego tenemos un break de 11 a 11:30. Esta vez lo tenemos media hora más tarde. Y luego tenemos de 11:30 a 12 la introducción a MODIS, de 12 a 1 el acceso y análisis de NDVI de MODIS sobre la cuenca hidrográfica de São Francisco Verdadero de Brasil, y luego el almuerzo de 1 a 2. De 2 a 3 la introducción a SMAP por el doctor John Bolton, de 2:30 a 3:30 el acceso y análisis de datos de SMAP, luego un break de 3:30 a 4. De 4 a 4:30, la introducción al acceso a la evapotranspiración por el doctor John Islander. De 4:30 a 5, el acceso a evapotranspiración basado en Landsat. Y tenemos media hora al final para preguntas, discusiones o retroalimentación. También les recordamos, nosotros enviamos el día de ayer un correo con una encuesta para que nos puedan ayudar a rellenarla. Tuvieron que haber recibido a sus correos. Y es un poco también como para conocer la audiencia, tanto la que está conectada en Zoom como la que tenemos acá en el salón, conocer también sus intereses y cualquier retroalimentación ahí sería ideal que lo puedan incluir en algún comentario o algún tema que les parece que es importante que lo abordemos durante estos talleres. Vale, entonces antes de la evapotranspiración, Perry.
Buenos dias, bon dia. Good morning, everybody. Is everyone rested from last night? Excited? Day 2? Okay. As Larissa mentioned, yesterday was more of a kind of didactic exercise, an introduction to some of the themes, and starting this week, we're getting into the thematic areas. So as we mentioned, we will be updating the materials on the GitHub as we go. So again, as you see, the latest update was made just this morning. So hopefully people who had installation troubles yesterday during the session, internet problems, were able to maybe do the GitHub install at their hotels. Is anyone still having issues with that? I'm not seeing any hands in the room. Hopefully the people online as well. So this morning, if everyone has time before we get started, we will be using some of the software and the coding packages that the Anaconda environment creates for this session. So it would be good to very quickly do this exercise to git pull the most recent files to your machine. And I'm actually going to show you an example of what that looks like. If anyone has any questions, I'm going to do it right now on Larissa's machine. So let's try this out. Okay. Any questions before we get started? No? Okay. So hopefully, again, at the hotel, Wi-Fi, when everyone wasn't downloading at the same time, was a little better. If you have the GitHub repository cloned to your laptop, you would first change your directory. Oh, here we go. Change directory into the GitHub repository. So I'm now in the files, and all I'm going to do is do git pull. And this should be a much smaller download. These are only taking the files from GitHub that we changed. So you can see what that looks like. Thank you. And we'll just let this load. So we've uploaded a couple presentations, some data sets for the sessions today. And this is what is now downloading to your machines if you're running these commands. Okay. We'll let this download for a little bit. And if there's any questions online, please do enter them in. Any questions in the room, we can troubleshoot. And we will get started with the first session at 7:15.
Si tienen alguna consulta, por favor, levanten la mano. Igual a los del Zoom, si tienen alguna consulta con este proceso, déjenlo saber en la función de preguntas y respuestas. Esto puede demorar dependiendo de la conexión a internet también.
Okay. Hopefully your files are still downloading. That's okay if it takes a little bit of time. We're going to show you what it looks like here as we get started for the first session. And I will really quickly activate my environment here. Conda activate Plata. Okay, you should see the activation here. And so I just wanted to give a very quick intro into a tool that we'll be using for this first session and a couple sessions later on in the week. This is a tool called Jupyter Notebook. Is anyone, we've had some Python experience. We have some coders in the room. People have used Jupyter Notebooks before? Okay. For those who are unfamiliar, I'll just give a quick overview about what these are and why they're so powerful. And all I'm going to do is type in the words Jupyter Notebook. It's Jupyter with a Y. And hit enter. Okay, this is what happens when you run Jupyter Notebook on your machine. It's going to bring up a browser in your, a window in your web browser. And you can see this is the file structure of our repository. And so what I will do is then go from sessions to the current session. Our first session in GPM, or in session 2A is GPM overview. And so actually, we're going to say the Jupyter Notebook, excuse me, for the practical exercise that follows this, but we're first going to give the mic over to Dr. Venkat Lakshmi, who's going to give an overview presentation on satellite precipitation. So, uh-oh.
Hey, thank you very much. My name is Venkat Lakshmi. I'm the John Newcomb Professor of Engineering at University of Virginia. So most of the work done in my group comes from my 12 PhD students and my postdoctoral researcher, Bin Fang, who is probably already online. But this talk on precipitation and understanding how GPM and other things characterize precipitation. And I'm not going to limit myself to just satellite. I'm also going to do rain gauge and radar to talk about how GPM and other things, other instruments characterize precipitation. We have to realize that there are experts at NASA, and the slides which follow are exclusively from those experts. I've tried to keep their affiliations on their slides. The first many slides are from George Huffman at NASA Goddard. He's the chief of the Mesoscale Sciences branch at NASA Goddard, and he's also the GPM project scientist. There are also slides from Gail Jackson and as well as Chris Komarov. Next slide, please. So precipitation. So it's so important because it's the largest principal component in land surface hydrology. So if you don't have hydrology, if you don't have precipitation, you have no hydrology. So many times when it's raining outside, I tell my friends and colleagues that rain is not a 4-letter word, but it's job security. Because, if you don't have any rain, you don't have any hydrology. So if you look at publications, you don't see too many publications on hydrology in Saudi Arabia. So there's no rain there. And measurement of precipitation is impossible. It's not difficult, it's impossible. Because it could be raining in your house and not in your friend's house. It could be raining for 5 minutes and then stop and start raining again. So anybody who says they know how to characterize precipitation is lying. So referring to gauge observations as ground truth, this is an old terminology, ground truth. There is no truth. If you think gauge observations are ground truth, you are completely mistaken. So please stop referring to as ground truth. And quoting one of my favorite actors, Jack Nicholson, in A Few Good Men. I do not know how many of you have seen Few Good Men. You know, truth. You can't handle the truth. There is no truth. There is no truth in precipitation. It's really difficult to characterize. So the only thing in surface hydrology which has true characterization is stream flow. Anything else is wrong. Rainfall is wrong. It's at a point. ET is wrong. It's at a point. Level of water in the aquifer is wrong. It's just at one point. And aquifer water level is so variable. So only thing true in hydrology is stream flow. And it depends on how accurately you measure it. And most places in the world, stream flow has been measured by even pre-civilizations for about a couple thousand years. So stream flow we have, everything else is not. And one of the things you should always remember is that precipitation is an input to models that simulate stream flow. So precipitation becomes really important. Now there is two other things. Larger time accumulations and larger spatial extent is always more accurate. So 10-kilometer monthly precipitation is much easier than 1 hourly 1 kilometer. It's obvious. And also, if you look for 100 years, total precipitation in a river basin equal to total stream flow. Very simple number. For 10 years, maybe 1 year, probably more difficult because there's infiltration, recharge, and changes in groundwater. But over 100 years, total precipitation has to become equal to total stream flow. Next slide, please. So I'm going to go into the first part of the talk, or all the talk basically. So this is all slides from George Huffman at NASA Goddard, and the other names of people are all written out there. People who have contributed to satellite characterization of precipitation. Next slide, please. Okay, so rain is easy to measure, hard to analyze. The same kind of stuff which I just told you right now. So rain is generated on a micro scale. You know, if you think of how rainfall is generated, it's not very straightforward. And the correlation distance and time is very short. So it's like, it's not very highly correlated. And point values only represent small areas or short time. So if you think of it, using a rain gauge is actually not at all accurate for rainfall. It's completely inaccurate for rainfall. Okay. And only a finite number of sample causes problems, because if you take all the rain gauges in the world, it's not more than let's say, let me make up a number, 100,000, and that's not enough. So it's just not enough. Next slide, please. So this is an example of July 1994. It's a monthly rainfall for the area of Washington, D.C. And all of these these contours show you different accumulations of rain. I think it's the rain is in inches in this one. And you can see that there is no correlation between locations. And there is a spatial scale over here somewhere, or maybe it's got erased, but there is, yeah, right here. This is 6 miles. This much is 6 miles. So if you go from one neighborhood to the other, not only is the rainfall different on an instantaneous basis, but it's also different, highly different on a monthly accumulation basis. Makes it very difficult. Rainfall is really difficult. And then to understand that we are going from the most difficult one in hydrology to do all these simulations. Next slide, please. So every way we measure or observe precipitation, we have errors. Rain gauge, there's wind losses. Rain is falling straight down and there's some wind and it goes away. So then you can't capture the rain with your rain gauge. There's splashing. Sometimes if you have the rain gauge filling up, it splashes over. So you lost that accumulation. Evaporation from rain gauges before it records. Side wetting. Sometimes the rainfall could hit the rain gauge on the side, and that's called side wetting. It does not account for that. And then, of course, whenever we use rain gauges, we always interpolate, and interpolation is all fraught with error. There are also errors in radar, satellite, and numerical prediction models. In the radar, the population, raindrop population equations, it's not very easy to characterize population in the beam of the radar. There's anomalous propagation, false echoes, blockage by surface features, and of course, the side lobes, which contribute to a lot of errors. In the satellite, there are errors due to retrieval, there are errors due to beam filling, and then of course, time sampling always has a lot of errors. Numerical prediction models, the models which are used to predict the precipitation for tomorrow or day after tomorrow, they have computational approximations because it's very difficult to solve the full-blown equations. They always approximate the equations before they solve them. They also have initialization errors, exactly trying to initialize the space and the time is not an easy task. And there are others in other parts of computation. Next slide, please. All right, let's go to the simplest one, rain gauge. So this is right out of the weather.gov website. This is how a rain gauge looks like. It's called SRG, standard rain gauge. It's 11-inch plastic or whatever metal a cylinder where you collect the rainfall. You try to place it far away from. There's all rules about where you can place a rain gauge. You can't just place it underneath your window because that would be wrong. So, okay, next slide, please. Okay, so in United States, there's a lot of rain gauges, and people don't realize that there's a lot of rain gauges. It's not just National Weather Service. It is other agencies as well. There are a lot of fire programs which have rain gauges. USGS has lots of rain gauges. The Army Corps has 1,600 plus rain gauges. National Weather Service actually does not have that many. It only has 200. And there are many, many other agencies. This is not counting the state agencies. The state of Virginia may have 100 rain gauges, state of Washington, the state of Oregon, all of them have rain gauges. And many of these states now are trying to develop something called a mesonet. Maryland just launched a mesonet. They're all fashioned after the one which started in Oklahoma in the late 80s and early 1990s called the Oklahoma mesonet. That is the gold standard of all mesonets. So there's a lot of other rain gauges. The spatial resolution of a rain gauge, as I said, is just a point measurement. So it's not going to be extrapolatable. You can interpolate between rain gauges, but it is not accurate. Next slide, please. Okay, so if you look at a rain gauge, and this is a rain gauge run by USGS in Sarasota, Florida, and this is long time ago. You can see this, and it's very easy to look at the web and get data from rain gauge, especially in United States. It's all free data, very easily available. The latency of the data is but a few hours in most of these places. So you can just go in and pull down the rainfall data. Next slide, please. So this is Jeff McCollum. I think he was at the National Weather Service. Jeff took a couple of rain gauges. This is, I think, somewhere in Texas, if I'm not mistaken, and plotted the rain gauges, rain rate, interpolating for the rain gauges every 5 minutes, rain rate in millimeters per hour. So you can see the rain moving across the gauges for this thing. But it's a luxury. It's very difficult to get so many rain gauges in an area. And most likely, this was an experimental area where they had a lot of rain gauges. Next slide, please. Radar, weather radar. Next slide, please. So in the late 1980s and early 1990s, the United States started investing in something called a Doppler radar. So the Doppler radar is interesting because it does not only give you rainfall amount, but it also allows to capture direction. It's just like a radar detector of a police car who can tell you how fast you're driving. So this is a Doppler radar. It's the next generation weather radar system called NEXRAD. And right now, I checked this morning, there's 160 of them in United States. Its range is about 250 nautical miles, about 250 miles. And they have dual polarization, H and V pole, send and receive. So it's very, very accurate and very, very good. And it also helps to detect frozen precipitation. Very important because in many parts of United States, especially in the winter time and in high altitudes, frozen precipitation is a real cause of concern. To issue real-time warnings to people driving cars that you should not be driving up to ski because your car may ski down. So applications of this NEXRAD include severe weather, flash flood warnings, air traffic. One of the other parts is many airports have NEXRAD so that the airplanes can be warned if there is too much weather. And the Radar Operations Center is based in Norman, Oklahoma. I go back to my earlier comment. Most of the mesonet, weather, water, climate, all originated in Oklahoma because of two reasons. One is Oklahoma is very productive in agriculture. They want to know, what's going on so that they can have good crops. And two, it's also very well known for severe weather. There's lots of convective storms in Oklahoma. The only time I have seen hailstones the size of golf balls hitting my rental car. Thankfully, it was my rental car. So it's very, very interesting place for origination of many of these measurement techniques. Next slide, please. Okay, so I think last night we were speaking with some people at the reception and they talked about radar. Radars have been there for a long time. Actually, the technology developed after the Second World War, and there is a lot of, they rework the radar, which they were using for military for rainfall, and they came up with this very simple equation called Z equal to AR to the power B. And it's called the ZR relationship. Z is reflectivity and R is rainfall rate. Now, this is not universal in the sense that yours A and your B will be different maybe for Argentina, Brazil, Bolivia, Uruguay, Paraguay, Chile, Colombia, all can be different. And it can also differ based on the type of the storm. Convective storm, stratiform, different storms can have different ZR relationships. Next slide, please. So for the United States, this is the coverage of all of the WSR 88D, the next generation NEXRADs, Doppler radars. Is pretty good. There are some holes where there is no coverage, but otherwise it is very, very good. It's a very good coverage of these radars. Next slide, please. Okay, so NEXRAD data have a lot of attributes, a lot of observations, which include reflectivity, radial velocity, and spectrum width. Now, for us who use the rainfall from the radar, the radial velocity is very important because it tells you if the rainfall is going away from you or coming towards you. And there are a lot of analysis. NCDC, the NOAA Climatic Data Center has lots of this data. And I actually just Googled this website in the morning. So I know this has an active link. So next slide, please. So examples of this, there is a lot of very good stuff with NextRad. I'm sure there's a lot of good stuff in South America also with radar. And I'm sure they have similar kind of application windows to see the radar, rainfall, etc., to visualizing, because the whole point of radar rainfall is to visualize it, to see where it is moving and how it is affecting. Because even if you have the same rainfall over a watershed, same rainfall, the direction of movement of the rainfall will change your stream flow. If the rainfall is moving from the outlet upstream, is different than moving from upstream to downstream. So the direction of rainfall is the most important part, and many people don't realize that. And that's why a Doppler radar is very good. It'll tell you the track of the storms. And if the track of the storms is known, it's much easier to estimate the impact of the stream flow. Next slide, please. This is an example of a hurricane, very, very famous hurricane in August of 2004 called Hurricane Katrina. And it flooded the city of New Orleans. And I think the pictures and stories of it reverberated for many years to come. Very important one. And this is how it looked, very, very large. The reflectivities, higher reflectivities means more precipitation. Next slide, please. Now, another thing is also that the NextRads have become even more fancy. Not only can they tell you the reflectivity in XY dimension, but they can also give you the Z structure. The reflectivity as a conical reflectivity, up. So give you different slices of the atmosphere so as to tell you where you are having the precipitation originating from. So this is really important. It gives you a three-dimensional view of precipitation. Okay, so now to recircle back, and we're just going to jump into satellite precipitation soon. Microwave imagers, good instantaneous results. Infrared is good sampling because microwave has lower spatial resolution. Infrared has higher spatial resolution. Soundings in cold surface conditions gives you information. Precipitation gauge, at the gauge, there's no bias. The model has a very good coverage because you can run your model everywhere you want, but it has to have the right physics. The biggest errors for rainfall is in mountains and snow and ice conditions. That's the most difficult, and that's the most important for weather advisories. Okay, so we talked about this side. Now come to this side, because now we are jumping into satellite. And when we're jumping into satellite, there's a couple of very important metrics, couple of very important definitions. First one is latency. How quick can you get the data? How quick can you get the information? And in the case of infrared, it is 15 to 60 minutes. It's very quick. But in microwave, it takes a little longer for transmission of it. What's the footprint? What's the spatial resolution? Infrared, thermal infrared, very high resolution, 4 to 8 kilometers. Microwave, low resolution, because the resolution of a microwave sensor is dependent on the wavelength. So, and the size of the antenna. So if you have a low resolution microwave satellite, like in the L-band, your antenna will be as big as a football in order to get high resolution. It's a very, very simple high school formula on diffraction. The interval of integration in the infrared, it is very quick, 15 to 30 minutes. Microwave satellites, much more difficult, because remember, microwave satellites are sun synchronous. So it's an AM and a PM overpass. But infrared, you can have something like GOES, the GOES satellite, which are all geostationary, and you can have, very, very quick 15 to 30 minutes. And in infrared, however, the temperature of the cloud top is sensed, and estimating from the cloud top temperature is how much it rains. In the microwave, it is actually the scattering of the raindrops. So it's a little different physics from infrared. Infrared is just looking at the temperature, Microwave is looking at the scattering. So it's actually looking at the raindrops. Of course, it does a whole bunch more physics. The scattering of the raindrops is at the cloud level. But by the time the raindrop comes to the ground, some part of the raindrop can evaporate. Some parts of the raindrop can coalesce with each other. So there are two independent physical phenomenon which is modeled to figure out rainfall at the ground surface. Next one, please. So looking at history, this is the history of all satellites, all sensors which have sensed rain since 1988. Since 1988. And it used to have this huge system called SSMI, Special Sensor Microwave Imager, at 19 and 37 gigahertz, which was launched in 1988 and 87, actually, 1987, and has continued till today. And they use those frequencies to estimate the precipitation. Now you can see over here, the golden era begins with TRIM, and we'll jump to TRIM in the next slide. TRIM, Tropical Rainfall Measurement Mission, and it has continued on so far. There is the Megatrophique, it's a joint satellite between France and India, and then GPM. TRIM, very, very important. It was the first mission dedicated for rainfall. So the SSMI series, which I showed you in the previous slide, was not dedicated for precipitation, but TRIM is and was, sorry. And it was a joint NASA, JAXA, a Japanese space agency mission, launched in November 1997 from Japan. And this is how it looks. It moves at about 7 kilometers per second. It has 3 instruments: TRIM microwave imager, precipitation radar, and visible infrared scanner. So 3 instruments to sense and predict the rainfall. Next slide, please. And now we have GPM. It's the gold star of all rainfall sensing satellite systems. It allows us to not only sense precipitation in liquid form, but also in solid form for snow and ice. And that is the biggest improvement between TRIM and GPM. Now, GPM has 2 distinct instruments. The mothership has 2 distinct instruments. One is GMI, Global GPM Microwave Imager. It has a whole bunch of passive sensors. And I think Sean explained the difference between passive and active sensors. And it is from 10 to 183 gigahertz. And the next slide, next. Next is a dual frequency precipitation radar. It has a radar which has Ka and Ku band, the 13.6 and 35.5 gigahertz. And it's like a CAT scan of the rainfall. So this is a really, really fancy instrument and a very fancy satellite bus. Next slide, please. So this is all the details you can find on GPM, thanks to George Huffman and Gail Jackson. You know, it has a very nice track record. It was launched in 2014. They thought it would last for 5 years, but it's still going strong. Supposedly had only 5 years of fuel, but it's still keeping on giving us observations, which is really, really meaningful. It has these 2 radar channels, Ku and Ka, and then it has all these frequencies in the passive radiometer from 10 to 183. It's very, very high resolution. It's 5 kilometer footprints for the radiometer as well as the radar. And in the radiometer, it also has a 250 vertical resolution. So as I said, CAT scan of the atmosphere. Next slide, please. So this is another cartoon. Keep clicking. So this is how it looks like. Ice scattering, rain scattering, all kinds of stuff it can see. And then the emission is one way. The radar is bouncing the waves off from the sensor, and the emission keeps on going from the ground. And this is all kinds of absorptions and emissions and scattering, which happens. Next slide, please. Okay, this is all the, when they make a radar, it's very exciting to see their clean rooms and all of this thing. And some of the targets they use to test the radar to see how it works properly is all these different roughnesses. And you can see these roughnesses out here. Next slide, please. Next slide. Okay, as I said, in GPM, I called that picture I showed as the mothership. That's the core observatory. It's one of many. So GPM produces rainfall every 3 hours. The way it produces rainfall every 3 hours is because it has many, many, many other satellites with which it coordinates the data. So the rainfall from GPM you see is not just from this. It is from all of them put together, and a very complicated code, as I will show you in the next few slides, and how it moves forward. So keep clicking because, yes, so the way you see it is, this is a cloud. There's a freezing level or a melting level. Above it is all frozen. Below it, it's all melted. So above it is all solid, and below it is all water. Next. So one more. I think we have a few of these, so you can keep clicking. Okay, yeah. So remember, I told you that the radar has two distinct bands, 13 and 35 gigahertz. But the radiometer is all the way from 10 gigahertz to 183. So from here to here. And so different parts of the radiometer do different things. The shorter frequencies or the smaller frequencies are emission channels, and the higher frequencies are the scattering channels. Rule of thumb, if you know the frequency of microwave in gigahertz, let's call 1.5 gigahertz, or let's call it 6 gigahertz, the C-band. All you do is divide 30 by 6, and that's the wavelength in centimeters. So 30 by 6 is 5 centimeters. So when we talk about scattering, the rule of thumb is an object can only scatter if its size is comparable to the wavelength. So when you go to 183, or let's say 200, the size becomes very small, because 30 divided by 200 centimeters is more like 1.5 millimeters. Okay. So there are many particles, rainfall, which can scatter the signal. So the scattering becomes a big mechanism for even passive microwave emission as you go to higher and higher frequencies. So don't think of scattering only for radar. Radiometer can also contribute to scattering. Next slide, please. So this is a passive, yeah. Oh. So this is a passive microwave at low frequencies. This is the one which is emission driven. So there's emission from the ground. It goes through this liquid water, then goes through this solid ice and goes to the sensor. So in your algorithm, you have to account for the ground, liquid water, and the ice. So it's pretty complicated. Next slide, please. Now at high frequency, the same thing is emission, but there's a lot more scattering, because the high frequency radiation, passive radiation, also gets scattered. So the high frequency radiation gets scattered by the hydrometeor. So you can tell the cloud's properties with respect to solid frozen ice in the cloud. Very, very important. And this is the active. Everybody knows the active. It is, it bounces, it goes down, bounces off the earth and goes back up. So, yeah, go ahead. So normally when we do passive microwave radiometry, we write an equation for brightest temperature using some number for cosmic background, 0.21 degree Kelvin. And go ahead. Go ahead. Go ahead. Yes, please. So this is the equation for microradiometry. Of course, we don't use this complicated equation, but for setting up the equations in the computer code, you use it. But for simple things like soil moisture, as John will tell you tomorrow, it's much simpler. Next slide, please. So all of radiative transfer, basically all of radiative transfer, all of the satellite stuff we do is based on high school physics. It's based on Planck's law and its approximation called Rayleigh-Jeans approximation. And then you also have an approximation for the cosmic background. So for soil moisture, the very, very simple relationship is brightness temperature is emissivity times physical temperature. For rainfall, it's a little bit more complicated because we are doing a whole vertical column where we are doing sensing. So can you forward? So this is the most important algorithm for GPM. It's called iMerge, Integrated Multi-Satellite Retrievals for GPM. Because remember, I showed it was not just the core observatory. There's many, many, many satellite sensors, which is integrated together to get GPM. And it's complicated because not only is the algorithm, and this is like several years ago, this slide was produced, it shows you how different locations, Climate Prediction Center, NASA Goddard, and UC Irvine all work together to make that algorithm to convert all the observations from all the satellite sensors into precipitation. So it's not a straightforward algorithm by any imagination, but as you will see in the exercise which follows this lecture, you will see you can easily download the satellite data and use it for hydrological applications. Now with iMerge, there's three very distinct products. One is called the early run. 4-hour latency means you can go online and look at the GPM for this 10 o'clock. So you can see 6 a.m. GPM information because it's out. Early run. Late run is 12 hours because they wait for all the microwave information. The early run is using, far lesser data. And then the last one is they merge a lot of precipitation information from gauges into the product. And it takes 3 or 4 months. And the global precipitation climatology center has all these gauge information. So they take it all and merge it together. But for most people, go back. If you're doing hydrological modeling, late run is more than enough. The difference between late and final run is very minimal. So you'll say, okay, so what is the difference? So this is for the ocean. Remember, one most important rule for precipitation remote sensing is rainfall over the ocean is much more uniform in space than rainfall over land. I said when I started that you may have rainfall in your house, but not in your friend's house. It will not happen over the ocean. It's very widespread. Hundreds of kilometers of rainfall, which is pretty uniform. So this is comparison of rainfall or ocean rainfall, 50 north to 50 south, and it shows you the GPM I-merge precipitation. This is annual average, and then this also shows you the GPCP, which is merging all the satellite data sets, all the rain gauge data set, global precipitation climatology project. They merge everything together. And this is the one, the green one is from TRIM. And there is obviously a difference between them, a big bias. Next slide, please. So this is where you compare precipitation from an atoll. So there are islands in the Pacific Ocean which were chosen by rainfall scientists to compare rainfall from the satellite to the rainfall from the gauge. Imagine an island 10 kilometers by 10 kilometers in the Pacific, have a couple of rain gauges. It can sense the rain of the larger Pacific Ocean. And so this is the rainfall from that rain gauge, and this is rainfall from the GPM I-merge for 2000 June to 2019 January, a long period of time. And it has many, many dots here, but it tells you some very interesting things. I-merge underestimates the low rates, lots of dots here, and overestimates the high rates. And this is over ocean, which is supposed to be easy. So imagine the land, very next slide, please. The land, okay, actually, one more slide. I can come back to this. Imagine the land where this is over Colorado, Nebraska, Kansas, Oklahoma, Missouri, and Iowa. The solid line is the I-merge final, not even late, final run. And the dashed line is from the multi-sensor, multi-radar, multi-sensor. It's so over the land, it's so difficult that it is biased on this diurnal cycle for the summer, June, July, August, 2014 to 2018. And you can see that it's so much difficult over land to get rainfall compared actually very closely with the radar. A previous slide, please. So this is an example. Go one more back and then it'll start. Yeah. So this is an example of the diurnal cycle of rainfall over Southeast Asia. So you can see the GPM gives you a beautiful picture of the rainfall. Next slide, please. Next, yeah. So there are some examples here. This is an example of Hurricane Harvey, which was in the end of August in 2017, using I-merge, the multi-radar, multi-sensor, and some infrared precipitation, etc. And this is, you can see some of them are similar, some of them are not. And then this is comparison of them with sensors, different algorithms, different things. And so there is so many precipitation products. Sometimes the one you have to use has to be something you are comfortable with and which you have calibrated or validated with your observations. Next slide. Okay, you keep clicking. I want to go to the last one. Yeah. So this is an example. Oh, this is an example, very interesting example. So we are comparing for one day for just the land, 2007, September 18th, rainfall from all the rain gauges to the rainfall from the GPM. And you can see, yeah, it looks similar, but there's no rain gauges in the Amazon rainforest. So, however, the radars or the satellite says there's so much rain there. So it's important to know many parts of the world, many parts of South America, there is no rain gauges. So you have to believe in the radar if it's there or the satellite data. That's the only source of data. Next. So there's more examples. This is from Chris Kumarov at Colorado State. If you look at these three, 1998 to 2006, you can see for global rainfall averaged over that time, it all looks similar. You know, you can see the ITCZ, you can see the rain over the rainforests. Looks similar. So at least the satellite is producing rainfall, which is okay. But if you compare the satellite sensor estimates, these are all different estimates, to gauges, CPC and GPCC are all gauges. The gauges are all da-da-da. And if you look at the extreme rainfall, the gauges are completely different than the satellite estimates. So then it is up to you whether you want to accept the gauges or the satellite. So most likely, it's better to compare where you have the gauge data with the satellite data and get some modicum of confidence before you start using the satellite data for locations where you have no gauges. So I think this is the last slide. Final closing words. I couldn't have said it any better than Chris. So microwaves are superior to visible infrared for instantaneous rain because microwave is giving you scattering and emission. Infrared is just taking the cloud top temperature and converting it to rainfall. And then you have some other caveats, but products using gauge adjustment. So you can always use these products and use and merge gauge data sets. And, you know, thank you very much. Questions? Yes, please.
Sorry. I have a question on if you have any like recommendation on the use of satellite precipitation, but for more focus on severe extreme rainfall events or studies or any analysis on that scale. Like,
actually, it's very interesting you say that. I have a paper. So by the way, whatever work we do at the university, everything is written into papers and all of them are on Google Scholar. So you can, all of my papers are open on Google Scholar. There is a paper which we compared for TRIM, not GPM, globally using rain gauges versus TRIM for extreme rainfall. TRIM actually did very well, and GPM will do only better because it has a better spatial resolution. Now, the problem is you have an extreme rainfall in the middle of a forest, but you have no rain gauge. How do you know? It's like that old story. A tree falls in a forest, will you hear it? So, as I said, too much reliance on rain gauges has been a problem. But now that the international community has done so much work in progressing satellite rainfall, I think it would be very advantageous to use it. And I think it does, because the only limitation for satellite rainfall is the spatial resolution. And right now with GPM, the inherent spatial resolution is 5 kilometers and the gridded data is at 10 kilometers. So if your rainfall, your intense extreme rainfall is only 100 meters, then you will not capture it. But if it is 2 kilometers, then the 5 kilometer field of view will capture it and it'll get reflected in the analysis. So it all depends on spatial resolution. And I do believe that the satellite will be able to capture the extreme rainfall. And that's a very, very good question. Hey, you know everything. Come on, you should not be asking questions.
No, thank you very much. Very simple questions, but you mentioned the early and the late products, but there's a third one, which is the one I'm using, which is GIS. What's the
You mean final?
No, GIS. Maybe it's a format thing, but I wanted to know, honestly, I'm not sure what's the different.
I've never heard of GIS,
Okay,
but
I'll show you later.
okay, there is early, late, and final.
Yeah.
The only difference between late and final is merging gauge information. And the
Okay.
difference between late and final is very small. We use late. We don't wait for
Yeah,
final.
if we need almost or quasi real time, we need.
Yes, that if you need quasi real time, you better use early or late.
Early, okay. I'm a little bit worried because you mentioned that GPM mission is coming to the end of its service life.
The fuel life.
Pardon?
The fuel was for 5 years.
Okay.
But I think it can
Keep moving.
Yeah.
Is there any plan to continue with a different mission?
So
We need them.
I have not heard two missions which are coming up at NASA, and I think John is not here in the room. So you can ask him this question because he's the NASA lab chief. So the two missions coming up right now is this month, towards the end, SWOT will launch. Don't confuse with SWAT, SWOT. Sir, ocean topography. That's very important because it'll tell you the height, the change in the height of 100-meter water surface between 20 days of the overpass. And then in one more year is NISAR, which is NASA ISRO Synthetic Aperture Radar, which is an L and S band SAR. So that's more for damage assessments, whatever. Beyond that, I actually don't know what's there. And I should know this because I serve on the NASA Earth Science Advisory Committee. But I don't know if I'm sure there is a plan for succession of GPM because it is so important. As you know, as I said, there is no hydrology without rainfall. So I just hope it will last. I mean, it's like SMAP. It's, it went offline, but it came back online. So I hope it will last for a long time. I mean, same thing, you can think about MODIS and the Aqua and the Terra systems. It's 20 years. I mean, now they're almost at the thing that they don't want to, they're giving serious thought to whether to support the missions with respect to data downloading and processing. It's 20 years. We have 20 years of MODIS data. So it's very remarkable because most of these satellite buses only carry about a few years of fuel. How it lasts longer, I don't know. I think it is conservative estimates and they are fuel efficient once they go up there. I don't know enough about orbital dynamics to expound.
Thank you. You mentioned that you have papers published, and also I saw the slide when it said the stream events are better captured by the rain gauges. So my question is that you have any paper related how the impact of the comparing the rain gauges in a hydrological modeling with the satellite.
I'm so happy you asked this question.
Yeah, because for me, I think as a run in the hydrological model is okay because Sometimes you don't have access to the rain gauges, and maybe you can download and see and run a hydrological and calibrate a model. And then when the rain gauges comes, you can calibrate better. But
No, actually, I'm so happy you asked this question because and again, John is not here, but the last, my last PhD student who, worked on this showed in a paper written 2 years ago that the stream flow simulated using satellite rainfall is better than stream flow simulating using rain gauge. Now, he investigated 6 catchments. Some of them were very small and some of them were big. And depending on how many rain gauges you have, if you have a small catchment and you have 2 gauges, if you have a big catchment and you have 3 gauges, then what happens is that when you simulate the runoff using the rain gauges, it's much. If this is the simulation using the rain gauge, the Q, and we found that if this is the observation, let's say this is the observation, then we find that and again, I think I made a mistake here. Oh, I don't think this is. I hope this is not permanent marker. But anyway, so I shouldn't write. So when you use simulation in a small catchment, rain gauge may be sufficient and more accurate than satellite. But in a little bit bigger catchment with not as much rain gauge density, satellite rainfall outperforms rain gauge by a mile. Huge difference. And
where those catchments were located, because the climate.
Yeah, 6 catchments in Vietnam. And actually, I have the paper on my computer. I can email it to anybody who wants it. It was published in March 2020 in Journal of Hydrology. It already has 60 citations. So it's a very unique thing. And I'm sure in South America, you can try sub-basins of La Plata and we can prove this. It's very, very simple.
Because also when you have your rain gauges, you have to clean the data. So it takes a lot of time.
Of course.
And you get excited and you want to run a model, and maybe you can.
And also, just because you have a rain gauge doesn't mean all the data you're getting from it is correct. Okay. Because as I said, the only thing in catchment hydrology which we can believe is the stream flow. Even that you can say, oh, maybe not. But at some point, we have to believe in something. Yeah. So the stream flow is the only thing which is the integrated response of the catchment to precipitation events. So that's the only thing which we can, say it's. And so even that, the SWOT will be able to do that from space. But the difference of stream flow based on the variability of the stage every 20 days. So, and that's not as accurate as measuring the stream flow every day or every hour.
Okay, thank you.
Thank you very much, Doctor. A few questions. First one is, if all of the data and all the systems are worldwide covering a spectrum, I mean, we are interested that it covers, of course, the Plata Basin.
Of course.
Then the second is, if have you made or somebody have made specific studies in La Plata Basin? And the third one is, if we have opportunities to make PhD studies with you in your university and your center, and how many? Yeah.